Hi there, folks, and thank you so much for taking the time to watch my talk about serverless application development. I know a lot of us are isolating right now and protecting ourselves during these weird times, washing hands, social distancing, all that good stuff. But today, let's kick back, relax, let's talk about some serverless application development stuff, and I have some stories to share and some knowledge to share with everybody. And if you're wondering who I am, that's me and my little girl. Hi, my name is Gareth McCumskey. I am a solutions architect at Serverless Inc., the creators and maintainers of the open source serverless framework, probably the most popular framework for application development using serverless. And I've actually been building serverless applications since around 2016, since the sort of beginning of serverless. And if anybody wants to ever get in contact with me, you can find me quite easily on Twitter. I love talking about serverless stuff and sharing experiences, discussing things with folks. So feel free to hit me up. And let's get started. So first of all, let's just go through what the point of this entire talk is about. Besides the really nice picture from the beach down the road here in Cape Town, what's the point of this talk? And the whole idea here is that with serverless being so sort of brand new in the development space, we need to find some way to share the stories that we're all experiencing, what these best practices are, what the gotchas are, what are the issues that people come across as they're building serverless applications. And the more that we can share these stories, the better we can all become as developers. So to get us started, let's start with getting started. And really the idea here is that when you're looking and you're interested in serverless and you want to find a way to use serverless in your organization, how do you get started? And the mantra that I'm going to try and bring across here is the idea of aim small and miss small. But what you really want to do is you want to find a way to use serverless to do something that is practical, that has an actual effect on your application, but isn't so critical that if something fell over and broke, it's going to cost you and your organization a lot. So really, the idea is aim small and miss small. And the idea, and what happened was back in 2016, when I first started using serverless and the serverless framework, I was working for an organization that was a small team of developers. There were only the two of us. I happened to be the lead of the team, which meant I could make a lot of the technology decisions. And really, the fact that there were only two of us working on this online sales platform for a multi-million-dollar travel company, where all the sales for this company happened online. They had no ties to travel agencies or anything like that. So this online platform was incredibly important. However, the online platform was showing its age. It was about 10 years old. The code had been reworked multiple times in various ways, and it was starting to show its age and was having some serious issues. So the decision was made that we had to consider re-architecting things. The other side of this is that there was no in-house DevOps talent at the time. Before I had joined the organization, the company had just gotten a third-party consultancy to set things up in AWS. So they had the typical three-tiered approach with the load balancer, a web application tier, and the database tier, set up with load balancers, replication, and so on, which was serving them well. This helped solve a lot of the problems that they were experiencing, but it still wasn't ideal because it meant somebody had to maintain this, and it was difficult to find and justify the cost of hiring a full-time DevOps professional if they weren't going to be used 24/7, but they were still needed. So this is where serverless started coming into this as a first test, taking a looking at service building that sort of hello world application with serverless. Things looked really good. I was able to get an API gateway endpoint that was triggering a Lambda function that was writing into a DynamoDB table, and then a relational database as well, which is something else I was trying at the time. And this all looked really cool. This looked like it was doing the job. It was removing a lot of the DevOps overhead that we couldn't manage as a team, or that we didn't want to manage as a team, because we were going to be very busy building our application and supporting it and supporting our users and the business. So serverless sounded absolutely great for this. But now we had to pick our first essential POC, a way to proof the use of serverless as an alternative to the existing incumbent technology. So we took a look around at our application and we decided to strangle out one particular feature set. And this was the review system that existed in the application at the time. So you can imagine for a travel agency, if you've got these really expensive, low volume sales products, you need to find a way to engender support in your customers to make them realize that, yes, this company does do travel tours. They have 5,493 reviews of people that were satisfied with the tours. So they're probably not going to renege on the promise once you've made the purchase. and the tours are probably going to be pretty good, high quality. So features like this badge that you see on the screen now is something that was used on the site on the homepage to get that trust across that this was a legitimate company with a good product that you could trust in buying. And this filtered down to the actual tour pages themselves, where you get the reviews for that specific tour, a nice little summary right up in the above the fold. And then later on in the product page, you can actually go read the specific reviews by people who went on that very specific tour. So this was an important feature, but it wasn't critical. If this feature happened to suffer some kind of mishap, it wasn't going to cripple the organization. Users could still purchase tours. And we could take our time rolling back to the previously working version. So this was a great target for our proof of concept. Again, we're aiming small and we miss small in case something goes wrong. Being inexperienced with something like serverless, you focus on something like this to begin with so you can start building that expertise until you get more comfortable with what you're doing. And ultimately, we ended up rebuilding this feature with serverless, and the impact of switching to serverless for this one feature was absolutely astronomical. It was way better than we could have ever expected. Just switching this one feature over to a serverless backend with a front end re-architected with API calls, we could actually see in New Relic at the time, we could actually see the reduction in CPU on the servers that were trying to run the application. The moment we turned this online, CPU usage dropped by a good few percent, memory usage dropped, and the time to load pages increased dramatically. So this was a great win for us. Serverless really came out tops here as a proof of concept with this specific feature. Again, aim small, miss small, prove the concept out, get some experience, and then you can start really rolling the ball out on doing much grander and bigger things. And that's where we ended up going. We decided to do some really bigger and greater things. And we started re-architecting larger portions of the site. And at the time, the infrastructure was using RDS as the data store backend, which is fine. RDS and relational databases is the sort of traditional data store that you have with web applications. And we wanted to continue to use this because that's where all our data was sitting. It was also a technology we were familiar with and knew how to use reasonably efficiently and pretty well. And RDS kind of handled a lot of the management of the relational database for us. But what ended up happening was we did not realize that there were some limitations with serverless and relational databases at the time. And this is where we came to a sort of one of our smaller sales periods inside the organization. And we decided to re-architect some portions of the site to using serverless and RDS at the time. RDS, unfortunately, back in 2016 had a few issues around using it in serverless. The biggest one of which was the connection limit. So, if you're not aware, these days things have changed, which I'm going to get to in a minute. But back then, and today, if you do architect things in a certain way, relational databases have a limited set of connections that you could use. And at the time, we were architecting our serverless backend as a collection of microservices. And we were attempting to follow the microservices paradigm of a distinct data store per service so that you don't have communication across the service boundaries using the same database. It's just a way to sort of secure data integrity, as it were. The downside of this is that every service had the smallest possible relational database instance running, which meant that the smallest one has about 60 connections. And when we went live with this during a sale period that had a few thousand users on the site all at once, very quickly we ran out of available connections on our relational database. Not something we could see in testing as a developer because we were running 2 or 3 users at a time. But very quickly we had a few thousand users coming to the site for a sale and our connections ran out and it just looked like the database had fallen over. A quick restart of the database instance obviously reset all the connections. Things looked great for a little while and then it all fell over again. At the time, the only way we got over this initially was just to increase the size of our RDS instance so that the available connections on that RDS instance was quite high. And this solved the problem for us so that we could see through the busy period. But we had to obviously come back to this later and look at how we could solve this problem. One of the other issues is the effect of VPC as well. And this is something we didn't realize initially because of the opaque nature sometimes of working with serverless applications is you can't see what the users are seeing a lot of the time. And at this, and back then, before the VPC changes that started rolling out November last year from AWS, VPC was a bit of an issue here because we could see up to 10-second latency sometimes for users as VPCs were being spun up, especially because of our use of relational database. So this was a bit of a problem for us as well, and ended up galvanizing us to look at how we could re-architect. These days, if you absolutely have to use a relational database, a lot of changes have been made on AWS to help solve these problems to a large degree. RDS proxy is probably one of the biggest ones that completely alleviates the whole connections issue. You can have yourself a T2 small, or is it T3 small these days? I cannot remember. With 60 connections exclusively. RDS proxy essentially connects to that with a single connection, and you use RDS proxy instead of directly connecting through to your RDS database, and that helps solve that problem. VPC has also been completely reworked when it comes to the Lambda situation, so that you're no longer creating a VPC for every single unique Lambda that gets created. So those 10-second latencies are basically a thing of the past. VPC and RDS do still have some issues with building serverless applications. So when you can look at alternatives, I would highly recommend it. And the obvious alternative here for folks who may have been building serverless for a while is DynamoDB, which is a really great data store for serverless, as it's a really high performance transactional data store that lets you connect to it without creating connection pools. You're essentially just making API calls. It's incredibly fast and really well suited to sort of serverless workloads. Moving on from that, one of the contentious topics that I hear a lot of folks talk about when it comes to serverless is the idea that serverless is incredibly expensive. And the truth of the matter, the truth of the fact is that serverless is not necessarily much more expensive than what you're traditionally using. If you try to take a carbon copy of what you do in a more traditional application and try to run that on serverless, you may start running into cost issues. But the vast majority of the time, folks don't actually add in all the costs related to the infrastructure that they normally run versus what you would run if you were building with serverless. Let me go through that in a bit more detail. So really, what I'm talking about, first of all, we cover the free tier idea, because a lot of applications in serverless can end up costing little to nothing, because a lot of the serverless services out there include very generous free tiers. Everything from Lambda to DynamoDB to API Gateway have permanent free tiers, not just limited to a year either, where you can sometimes end up paying nothing for your infrastructure. And I've actually built applications for customers. Then this is the bill that one of them got at the end of the month. And this isn't the first month after we went into production. This was a couple of months ago. Now the project has been running for about a year. And the only reason that they're getting any bill whatsoever is because of DNS queries through Route 53. 58 US cents for an application that does thousands of requests a day, only because they haven't yet breached the free tier on API Gateway, Lambda, and I think it was, API Gateway and Lambda. Pretty compelling stuff if you don't have super high volumes. You can run incredibly cheaply. But really low volumes isn't necessarily what folks are looking at when they come to serverless. They want to find ways to reduce the overhead of managing large-scale infrastructure for lots of load. And this is where the next idea that you can scale to zero and save yourself a lot of money, especially if you're in the environment with lots of bursty workloads. For example, if you run a very localized web application, maybe you run an e-commerce store that only operates in South Africa, as happens, as companies I've worked for. And at 2 a.m. in South African time, there's no traffic on your site. Yet you have three EC2 instances up and running, spread across 3 availability zones, with a load balancer in front of that, 2 caching servers to provide you some caching, a relational database, a really big relational database, because you have to vertically scale this to the maximum predicted load that you may have in your database, just in case you hit that, and maybe a bit more for some headroom in case it's even higher. And then obviously a read replica on that, so that you have some kind of redundancy in case the master goes down. And now you're paying for all of this infrastructure that's essentially sitting around and doing nothing for you. Your traffic only starts at 8 a.m. in the morning, for example. Scaling to zero means that you save all of the cost of all of that complex infrastructure that's just sitting around and using up your bill. But then there's the other aspect of total cost of ownership, when you actually factor in the cost of people. People are incredibly expensive. A lot of organizations will look at the AWS bill at the end of the month, switch to serverless, then look at the AWS bill again and see that it's a bit higher, and not realize that they've saved money in other areas and actually enhanced their ability to be agile as well. So people cost money. And If you look at situations where if you're using EC2, if you really optimize your usage and cost of EC2, you can probably get your total infrastructure cost really low, much lower than you could potentially get on serverless because you use things like reserved instances and spot instances. But knowing about reserved and spot instances and how to configure that and set that all up doesn't come for free. Your agility could be sacrificed because now, instead of a developer being able to just grab the usage of an S3 or a DynamoDB table or an API gateway endpoint, a developer will have to either do it themselves or wait for somebody in the DevOps team to go ahead and set up this infrastructure for them for whatever they may be building. Maybe you need an extra caching layer or some additional storage space. I have to now wait for somebody on the team to provision this infrastructure for me, and I cannot deploy. I cannot get my stuff out there. I cannot actually add value to my business because I need to wait for all the stuff to be constructed for me. Not to mention the fact there is actually a massive shortage of skills out there in the DevOps environment for people that are qualified to do this. I might be able to spin up an EC2 instance and throw Ubuntu on it and maybe install Apache and some configuration. But for a really busy, high-volume web server, I don't necessarily feel like I'm the most qualified for that. I'd rather have somebody who knows the ins and outs of all of these systems and can build them up more efficiently than I can. But those kinds of people are in very short supply. And they're not cheap either. This is just an example of the average DevOps engineer salary. And this is something I grabbed, I think, 2 weeks ago, that the average DevOps engineer in the US is $135,000 a month. Obviously, this is regional. This is average in the US. The average in the UK and in South Africa would be different. But it just gives you an indication of what the cost and rarity of these types of people is like. Imagine if you had one DevOps engineer on your team costing that, how much you could use that, how much you could build with that kind of money, how much infrastructure in serverless you could use, and how much agility you would have in your team if developers could just provision out what they need to get the job done and start adding value to your company. So from one contentious issue to the next, this is something else that I've seen folks talk about where cold starts ends up being something that gets mentioned in the conversation. And somebody will make the comment that they ran their hello world application, and oh boy, when they executed that, when they called that API gateway endpoint, that Lambda function took 1.5 seconds to respond. That is way too slow. That latency is way too high. This makes serverless completely useless. When the actual fact is that specific cold start would have happened once and never again because they now had a warm Lambda function. And in my opinion, looking at cold starts and the effect of cold starts over applications over the years, I've noticed that cold starts actually have far less impact on the performance of your application than you might think. So what do I mean by that? Let's look at an actual example. So I'm working at an e-commerce provider a couple of years ago. We implemented a serverless feature that resulted in an API call being made to a serverless backend for every page load, every time a user loaded a page. And this example on the screen here is when there was a sale happening and we had approximately 10,000 simultaneous users on the site, constantly busy loading product pages, adding things to shopping carts, checking out, loading more pages, and so on. So really busy activity on the site, about 10,000 users, and every page load resulted in a Lambda function being executed, the same Lambda function every single time. So I decided out of curiosity to keep track of what the concurrent Lambdas looked like across 2 weeks of time with varying load. And this is the effect of one of those days, one of the busiest days in those 2 weeks with about 10,000 simultaneous users. And the number of cold starts that happened as those 10,000 simultaneous users dropped onto the site within approximately 4 to 5 minutes there were about 7 cold starts in total, which is very, very low. If you look at the fact that you have those 10,000 users within 5 minutes, only 7 of them may have had a slightly delayed execution on a Lambda function, maybe of about a second. That's incredibly low. If you think about the effect of a noisy neighbor situation on an EC2 instance, you have one line of badly coded code somewhere that's maybe it's a really bad SQL query that now needs to be sorted in code that can then cause a delay on other threads and other users on that one EC2 instance. This kind of delay is actually meaningless in that type of context. But you might be thinking, Gareth, that's only one data point. That doesn't prove anything. So I've spent time looking further. Now at Serverless, we have a monitoring platform that we provide to users with a free tier so that anybody can sign up and use this to monitor their serverless applications. And we use our monitoring platform to monitor our monitoring platform. A nice bit of inception happening there. And looking at a 24-hour period, one Lambda function was being executed 3.5 million times over a 24-hour period. That's a pretty large quantity of usage on that. And I decided to take the same period on the same Lambda function and just filter it out to show only the cold starts for that Lambda function for the same 24-hour period. And it resulted in about 944 cold starts in that 24-hour period. Obviously, you can see there's a massive discrepancy in the number there. That's only about 0.03. Let's just round it up to be generous. Of all of the functions, 0.03 were cold starts. That means that 0.03% of all the Lambda functions that were invoked over the 24-hour period may have had a delayed execution of around about a second, which is absolutely nothing. There's almost zero impact to any users on the system there. Most users in that 0.03 realm wouldn't even have noticed the additional latency, because the next time they load a page, the latency is gone because the Lambda functions are nice and warm. Really very little impact here. And obviously, the more astute of you will mention that a high volume site will obviously have less opportunity for Lambda functions to grow cold, and that's true. So let's take a look at what happens if you're in a situation where you absolutely have to reduce that cold start. What if you are in a slightly lower volume, so you have a greater proportion of cold starts in your Lambda functions, or you are just in a very latency sensitive environment? That means you cannot suffer even a 0.03% cold start, for example. There are ways you can mitigate a cold start anyway. So the first one, and this is sort of increasing order of effect, if you want to say. The first one that is often recommended is to find ways to decrease the package size of the Lambda functions that you push into AWS. Personally, I haven't seen as much of an impact on this, but this is potentially a free way to just put very small and minimal package sizes into AWS. It can have other benefits besides cold start reduction. So go ahead. This might be something that you find useful. You may find this actually improves cold start times of your Lambda functions. Personally, I haven't seen massive increases, but it's free and you can go ahead and do this. There are some great plugins with the serverless framework, for example. You can just include those plugins and they'll automatically start giving you these highly minified packages. The next step up from that is just increase the memory size. And while this may have an impact on your bill, the impact of increasing memory size isn't just an increase in the actual memory allocation in your Lambda functions. What some folks may not realize is that when you increase the memory size of a Lambda function, you are also increasing the CPU allocation linearly. So if you double the memory allocation, you essentially double the CPU allocation for that Lambda function, which is pretty neat. It also increases the network allocation. So the ability for the environment to pull the runtime and your code into the virtual machine goes up because the network speed is a lot higher. There's been a lot of research on this. There's a lot of folks who have published research, Medium articles, and so on about the effect of increasing memory size, and it does have a pretty substantial impact on the performance of your cold starts, of your Lambda cold starts. The other upside of this is that not only do you reduce cold start times, but you also increase the performance of your Lambda functions as a bonus. So hey, you reduce cold starts and you get faster executing Lambda functions. Pretty neat idea. And then on the other side, on the other extreme, you can actually completely eliminate cold starts if you wish. If you are willing to pay for the elimination of cold starts, there's a new feature released by AWS in November last year at reInvent called Provision Concurrency, where you essentially ask AWS to always keep X number of Lambda functions warm for you, because maybe you do expect that surge of traffic that's going to generate a bunch of cold starts all simultaneously. Just pay up front and you can get warm Lambda functions ready and waiting for that surge of traffic so that they don't suffer that cold start. And you can configure this in ways that turns this on and off so that you don't maintain a provision concurrency 24/7 for an entire month, costing you more. But ultimately, this is going to cost you some money. So really, it's a case of how much are you willing to invest upfront in infrastructure cost versus how much are you willing to suffer a bit of a delay on cold starts for some of your users. The downside of provision concurrency is that you are starting to slide more into the EC2 territory, where you have provisioned capacity up front that you're paying for by the minute. But again, it's up to your use case. If you need that reliability, that reduction in cold starts, then you can just go ahead and pay for that as well. So here comes an interesting issue that came up. It's come up a couple of times building serverless applications, and it really started back when I wanted to build an authentication service, and I needed some way to generate to generate encrypted tokens, encrypted passwords, and so on. And usually the library of choice for most frameworks is the Bcrypt library. And Node has a very handy Bcrypt library that you can use to create encrypted passwords that you can then store in a database. The problem is that developing locally and testing locally, this looks great. It works well. You can use Bcrypt. It's pretty speedy. It's a nice module to use. Unfortunately, it relies on a C library that works with it in order to make it nice and fast and efficient. And this is a library that's not available in AWS Lambda by default. So going ahead and deploying this application using the sort of native Bcrypt module available in Node, I ended up throwing errors because it did not find the library in the virtual machine that Lambda runs in. So now we had to find an alternative, and this is where you find the downside of sort of binary applications that require pre-built libraries to be available. Ultimately, with Bcrypt, this is relatively easily solved by using a JavaScript-only implementation of Bcrypt known as Bcrypt.js, very unique name. And it works incredibly well. It's going to be slightly slower because it's not a native binary that's built on the machine itself, but it is fast enough to get the job done. And if you need it faster, again, you can just up the memory allocation to increase CPU, which makes this run a lot faster. And you've got your problem solved. You now have a way to do Bcrypt. But this isn't limited to just this module. Funnily enough, we tend to see, I personally have had experience trying to run headless Chrome inside of Lambda, and I do see this from time to time from users, just in general, that the idea of using Chrome headless in a Lambda environment seems very attractive. But the Chrome headless binary is, again, a slightly difficult one to execute. At one point, we were using this to run end-to-end testing inside Lambda functions, and then Chrome updated itself, which meant that this binary got updated as well within the package that we were using, and it broke. Chrome started requiring the inclusion of additional libraries within the operating system that just doesn't exist inside Lambda, and so our tests kept failing now. We could not actually execute with Chrome. The only way we were able to solve this was to roll back to a previous version of Chrome, which meant that our end-to-end testing now didn't use an up-to-date version of Chrome headless, which, isn't the greatest, but it meant that things were still running. Although this problem, I know, has been resolved recently with some really nice work with Lambda layers and including a Chrome binary in AWS that actually does work up to the most recent version. So that's pretty cool. And there were other features that AWS has added to help this, because one of the other issues that I've had in the past is trying to get custom runtimes to execute inside Lambda. Again, the issues with specific libraries not being available in Lambda for those runtimes. But this has now become less of a problem because of AWS or of Lambda layers. And layers allows you to essentially bring your own runtime. It's a very nice feature where you can choose a custom runtime supported in frameworks like the serverless framework, for example, where you can essentially just point at a Lambda layer and run and write code that can execute on that runtime. It's a pretty nice feature, and it means that if you are looking for custom runtimes, you no longer need to worry about building your own binary and compiling it with all the features included that you need from scratch, like you would have had to in the past. You can pretty much use an existing Lambda layer that provides all the features that you need to use that runtime inside Lambda. It's a pretty useful feature. So over the years, you're building your serverless application, and you've started out and you've got this really nice set of Lambda functions with API gateway and maybe multiple other events, and this thing's growing over time. You're generating a really nice looking Lambdalith, as it's known. And then you hit across a issue when you try to deploy, and you get an error from CloudFormation that says you've reached the maximum capacity or maximum number of resources for a CloudFormation stack. And this is a real issue that I come across very regularly and have suffered myself as well in the past, where the single service that you're building, that you're deploying into AWS using CloudFormation through services like the serverless framework or even SAM, and you hit this 200 resource limit that exists in CloudFormation. And let's put this into context. Let's actually understand why this limit exists. So CloudFormation has this limit of 200 resources max per stack. And it exists for a very good reason if you think about it. CloudFormation was originally developed as a tool for DevOps. It wasn't a developer tool. CloudFormation is a way to deploy infrastructure into an AWS account with state and a way to manage the current state of that set of infrastructure. Lambda was released along with API Gateway, and serverless frameworks like the serverless framework realized that the CloudFormation service was a great way to leverage the sort of state management of a serverless application in the cloud, because that work was done by CloudFormation, and we could just deploy on top of that, use that as a way to help us deploy our applications as developers. But CloudFormation, as I said, wasn't built with developers in mind. So the number of resources that you need as a developer with all the Lambda functions and API gateway endpoints and all these other bits and pieces is far more complex than you would typically find in a DevOps environment. So a 200 resource limit was put in place so that if for some reason somebody was accidentally spinning out too many resources, 200 EC2 instances, for example, there was a hard stop here to prevent people from going overboard and potentially wiping out their entire bill. A very sane reason to have a limit. Unfortunately, this causes problems when you're building a serverless application. So just to give you an indication of how this can have an effect is if you take a look at the serverless framework, if you have one Lambda function defined with a single API gateway endpoint, that combination uses up about 7 resources in your CloudFormation stack. Very quickly, you can see if you have start hitting about 25 to 30 Lambda functions, each with an API gateway endpoint, you're going to hit a 200 CloudFormation limit. That can happen reasonably quickly. But there are ways around this and ways to mitigate this. So I'm going to go through a couple of these in, again, increasing order of preference, in my opinion, and in ways to resolve the problem. But typically what this usually comes up with folks who have now developed their application in a single service, and they want to deploy a new set of features that have been developed, and they hit this error message about 200 resource limit. Now what do you do? So the first port of call that I often recommend folks to take a look at is something called the nested stack plugins. There are a number of plugins available as part of the serverless framework that allow you to leverage the use of essentially nested CloudFormation stacks. The idea being that you can take some of those resources out that you need to deploy, put them into one CloudFormation stack, which is way under the 200 limit, take another set of resources out and put that into a completely different CloudFormation stack, and then nest those within a third CloudFormation stack. So you have a parent CloudFormation stack with children CloudFormation stacks. A pretty neat idea. And these plugins can help you get over this initial hurdle of having this resource limit. However, there's some downsides to the solution in that it does re-architect a lot of the sort of structure around how your application looks and works. So it can have impact on other solutions you try to use in your service. So it might not be ideal in this situation. It can affect monitoring tools who are not attuned to the idea of multiple stacks nested within each other. So in the long term, these nested stack plugins are not necessarily the best solution because they can hinder and cause some issues further down the line. But these are really great if you're stuck with this problem and need a solution right now so you can get the stuff out that you need to deploy, and then you can come back later and take the time you need to fix the problem on a long-term basis. So one of the techniques we see folks using as well as another sort of stepping stone to a much longer-term solution is the mono Lambda approach, often called the Lambda lith as well. And the idea here is that instead of multiple API gateway endpoints pointing at multiple Lambda functions, you potentially have a single API gateway endpoint pointing at a single Lambda function. And instead of API gateway being the routing mechanism across your code, the single Lambda function will then route across multiple functions, potentially, very similar to Express or Flask. And the mono Lambda approach is something we see often with folks who have built an application using Express or Flask and want to get into serverless. And the mono Lambda approach is a really great stepping stone to sort of lift and shift your existing Express or Flask application into serverless to get some of the serverless benefit. But it's also an approach if you're hitting this CloudFormation limit. So you can reduce some of the resources that are actually consumed, deploy this, get under the 200 resource limit, and now you have a bit more headroom to work with. You have a bit more time on your head to solve the problem again in a more longer-term strategy. The next step here, though, is ultimately sort of the best practice that seems to be coming out in this way is using the idea of micro and macro services. And microservices has been a bit of a contentious topic over the years with people for and against this pattern. The usual argument against a sort of microservices environment is the sheer amount of infrastructure complexity that this adds to an application. So whereas organizations like Uber, for example, that have been using microservices in a really big and successful way, their engineering discipline is large enough that they can manage the infrastructure burden that this imposes to reap the benefits that this architecture gives them. So it's really great for them. But when you're a smaller team, you're not an Uber, you don't have hundreds to thousands of developers on your team, microservices can still be a beneficial architecture. And using serverless means that you're removing essentially the infrastructure burden needed. You no longer need to build Docker containers spread across Kubernetes clusters with multiple EC2 instances and load balancing and all of the headache that comes with that. You can use these serverless services repeatedly in a collection of microservices that together combine to give you the feature set for your full application. It's a pretty compelling way to build your serverless solution. Works incredibly well, keeps you below your 200 limit in all cases, and means that you now have a very flexible way to manage the feature set of your application with less brittleness when you're deploying, managing across multiple developers potentially. It's a really compelling way to build applications. And with serverless, again, you've removed that infrastructure overhead, and yeah, you've solved the 200 CloudFormation issue at the same time. So one of the things that Lambda gives us, and this is pretty much the most impressive part about Lambda, in my opinion, is the idea of the Lambda Supercomputer. And really, the power that a supercomputer has is not necessarily just the ability to execute a single thread really, really fast, but it's the ability to execute lots of threads together in parallel really, really fast. And Lambda gives you that in spades. And this is something that you can utilize to your own benefit. So don't forget the absolute monstrous parallel nature that you can get out of Lambda functions. And I'm going to give you a concrete example of how this has been used in an organization that I was working with. And load testing is a really powerful application of this. And there are many, many more. But the idea here is that as a part of an e-commerce organization getting ready for Black Friday, you've got the set of infrastructure that you think may be able to handle the load that you're expecting to have on Black Friday, the biggest sale day of the year. You do not want to go down. You want to be able to reap the benefits of this day, this one day of the year. So you need to find some way to make sure that your infrastructure can handle this. So you spin up a staging environment with a replica of the infrastructure that you're planning on using on Black Friday, and now you want to test load on this. You want to simulate users on this test infrastructure to see how it can handle the load. However, it seems that generating simulated users in large enough quantities is actually a pretty big problem to solve. And we went through a few iterations of this. And first we started with looking at running our own EC2 instances. And as a part of this, we had the organization had somebody that was building end-to-end tests using first of all, the e-commerce platform was built on PHP. So we had an end-to-end testing platform running on Codeception, which is a PHP end-to-end testing platform that allows you to essentially simulate users loading a web page, clicking on links, adding items to cart, going through the checkout process, and so on. And you can, and by executing this end-to-end test, you're essentially simulating user traffic. You can add some randomness into the time to click on items, randomness into the product selection that was made, randomness in the timing to go to a checkout, and so on. So you can add some bit of variability, simulate user activity, which is great. And it's a great way to test that your application is working as intended. So the idea was to use that end-to-end testing as a way to simulate users. We just needed to find a way to run a lot of these threads in parallel. So the first attempt was to use EC2, and this became incredibly difficult to do because while we could spin up very large EC2 instances, getting the actual number of simulated users in parallel that we needed was incredibly difficult. Trying to coordinate all of these simultaneous users and multiple threads running in parallel was a very difficult task to perform. We couldn't actually figure out how to do this properly. So the next step for that was we realized that this couldn't have been a problem that only we were trying to have, that we had. Surely other people wanted load testing. Surely there were vendors out there selling a solution. And there were some vendors out there. However, our research showed that there were vendors that were very expensive and had very limited numbers of simulated users they could give us. So our search for a vendor to solve this problem was actually very short-lived. There was no vendor that we were happy with, and any vendor that we found that might be able to reach the number of simulated users we were looking for was asking thousands of dollars per test run, and that was just far too expensive for our usage at the time. So we moved on. And this is where we looked at Lambda. We looked at serverless as a way to potentially solve this problem. And bearing in mind that this is a new concept to us as well, using Lambda in parallel, conceptually we could see this happening. We knew we could get up to 3,000 concurrent Lambda functions running at the same time. Technically, it was available to us as part of our AWS account. we got that limit increase, so now we could go theoretically up to, I think it was 5,000 burst and up to 10,000 over time. So this was some pretty nice parallel workloads. However, now we had to get PHP running on these Lambda instances. So this takes me back to that sort of binary issue that we were having in the past and that I've talked about previously, as well as this codeception tool and the end-to-end test. And getting this all running was great. We could get this running on a Lambda function. We could actually send a simulated user. But now we needed to coordinate this. And this is where you start looking at the other services available to you in AWS. What we ended up with was a solution where you could have one API gateway endpoint where you could pass it a payload that tells it exactly which website to run traffic on, which end-to-end test to actually use, potentially even which runtime to use. So we had the options of multiple different PHP runtimes available to us. And this API gateway endpoint calls a Lambda function. The Lambda function will then put out, essentially create a SQS queue, this Lambda function will then put 15,000 messages into an SQS queue, and this would then spin up as close as possible 3,000 Lambda functions running simultaneously. Each Lambda function taking only 5 messages with a batch size of 5. So using SQS, we were able to coordinate 3,000 Lambda functions running concurrently with 5 users each. We had a brief wait period in each Lambda function so that we could wait for all the others to come on ramp as well. And these Lambda functions would then begin executing their test loads. So the end result was absolutely spectacular. We ended up having 3,000 Lambda functions running in parallel, or as close as possible as we could get. And technically, you don't have to have all 3,000 exactly running in parallel. We wanted to get as close as we can to simultaneous users browsing the site. And each of those Lambda functions could run 5 simulated users in parallel on the single Lambda function. We ended up using the maximum size Lambda function to do this, so that we had a really powerful CPU running there, as well as really good network capacity and memory, obviously. And this meant that, and we could actually get up to 10 users running per Lambda function, but occasionally a user would drop off. We'd have some failures, so we dropped it down to 5 just to keep it stable. And then there was more than enough for us. Your mileage may vary. You may be able to get far more users on a specific Lambda function. And this meant that we could run 15,000 simultaneous users executing on the staging environment for us to test the effect of this load of users spinning up within minutes. And every test that we ran on the staging environment cost us only about $60 in total. And the biggest cost there was the execution time of all the Lambda functions, because each Lambda function ran for approximately about 3 minutes. So we had about a 3-minute timeout on these Lambda functions running at the 3 gig full capacity Lambda function with 5 simulated users, $60 per test run, which was cheaper by an enormous margin than any other solution that we could find. And the result was that we ran this test once. We realized that one piece of our infrastructure was falling over from the load. Adjust that configuration, change that one piece of infrastructure, run the test again. Now something else. That infrastructure was handling it fine. Something else had fallen over. Adjust that, run the test again. Everything seemed to run fine. All the users were able to check out as needed. That means that we now had a resilient architecture that we felt confident using on Black Friday. And on that Black Friday, nothing fell over. It handled the load because the number of users didn't exceed 15,000. And because we had tested it, we knew that things could work. It was absolutely magnificent to see. And it meant that any time in the future, we now had just an API gateway endpoint that we could point at a staging environment and say, create users and go DOS that environment and see what happens. Absolutely awesome way to test our application. There is a downside to this, though. Lambda is incredibly powerful, and Lambda can do things in parallel in huge amounts. But if your downstream systems aren't ready for it, and that was the entire point of load testing, was to make sure that downstream systems can handle the traffic. But if you're not aware that this parallel nature exists in Lambda and that it can pretty much just eat whatever you throw at it, you could seriously drown out your downstream systems. And this happened to us in 2017, back at the travel agency, where we were preparing for the end of year or the mid-year sale time. And the travel agency had an massive annual sale where they were introducing the new tour dates for the coming year with some nice discounted prices, and thousands of users would be clamoring sort of on a countdown for the bookings for this the sale to open, so that people could go and buy the tickets for the sale that they wanted at the cheap prices. And every year before that, there happened to be failures. There was always a failure happening at the booking engine layer of the online platform that just couldn't handle the load. And this year we decided we're going to re-architect this in serverless. Let's make sure that this booking process is rebuilt using Lambda and API Gateway so that it's not going to fall over with the same problems again. We knew we could handle this. We had increased our Lambda concurrency limit. We were no longer using relational databases. We were using DynamoDB to help handle that load for us. API Gateway was going to be beautiful. It was going to be magnificent, and we were right. Our system stayed up for the first time in years running this mid-year sale. It was beautiful. Things were going amazingly well. Unfortunately, we used a downstream third-party provider that actually handled the sort of booking allocation for us, and they fell over from the load because they had never seen they'd never seen us actually send that much traffic to them before, because our systems had usually fallen over long before theirs could. But we were sending them thousands of requests in less than a few seconds, and their systems couldn't quite handle that, so they ended up throttling us, which meant that we were throwing failures back at our clients because we weren't architected to handle being throttled from our downstream providers. So this is something definitely to bear in mind, to make sure that when you have systems that could result in a lot of parallel requests going to downstream systems, you need to find ways to handle this. And there are a few ways that you can do so. These are a few of the techniques that we ended up using as well. The first one that is really, really useful is just find a way to debounce that incoming traffic. Just manage the herd of traffic that is coming at you. And in our case, what we found that year after this, we introduced some techniques to help just flatten out the curve of traffic, because in years prior, what we ultimately had was a booking page you could go to. You could go to the tour date, find that lovely tour that you want to go to, and you'll see a countdown timer before the booking button is available. So you're sitting waiting for this countdown timer to reach 0. Suddenly the booking button is now available. You click that button and off you go, and everybody's clicking that button at the exact same time, making that booking, and that's when the downstream booking provider falls over, because everybody's clicking that booking button at the exact same second. Huge amounts of traffic being pushed to that downstream provider. Instead, what we did now is that we added in a registration page, so you can see the button that is available to register, to sign up, to book your tickets for the sale, is now on a countdown timer. So instead of going to a downstream system that could potentially fall over, you need to click into the form, type in your email address, tick, 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 tick. You need to go to the password field and type in a preferred password, maybe a name. In the meantime, 5 other people have already done this. There are 10 other people that are going to do this just behind you, another 50 just behind them. And you're slowly filtering these folks through. You are now giving them, essentially putting them through a filtering process that's slowing people down a little bit, so it spreads the traffic out a bunch more. A really great way to do this. We even went to the point where after registering, you'd go to a page that lists all the available bookings that you had available. So you still had to now scroll through a bit, find the one that you're interested in, go through to the product page for that, now go find the actual date. So it is a great way to filter this traffic through while still keeping people excited with a countdown timer that they can then go through and start booking the seats that they want. The other advantage you've got is that you're in the cloud. You're in AWS. You have services available to you that can help you also manage this kind of traffic in a much cleaner way. And these are other techniques that we ended up using as well. With features like SQS and Kinesis, and even SNS to some degree, you can receive these booking requests. In our case, we were getting a lot of booking requests still really quickly. So we used tools like SQS and Kinesis to receive these booking requests without actually still pushing them down through to the booking provider downstream instantly. We were able to batch these requests, and we were able to still process them relatively quickly. Some requests would take a few seconds because we needed to have Lambda functions that could manage this traffic in a certain batch size and quantity of concurrent Lambda functions. And this is where using something like reserved concurrency becomes really useful. If you have 10,000 SQS messages gets dropped into a queue, you set a batch size of 10, so no more than 10 per Lambda function executed at a time. You set a reserved concurrency of 100, so that those requests don't swamp out your downstream providers. You're not hitting 3,000 concurrent Lambda functions all at once. You're only getting 100 concurrent Lambda functions, doing batch sizes of 10. This is a far more manageable process to go through, and it'll take you a bit of time to get through that queue, but you're guaranteeing that nobody's going to receive a failure. Your downstream provider is going to love you. Great ways just to handle this kind of stampeding herd situation. And that's really my talk, folks. Thanks so much for spending the time to sit and listen. If you want to get in touch with me, I love talking about serverless application development. If you have questions, if you're looking to get started, if you want some advice, feel free to send me messages on Twitter at GarethMCC. I am freely available there. If you prefer email as a communication platform, feel free to contact me at gareth@serverless.com. And please stay in touch. And I believe I will be switching over to the live version of myself now for the question and answer session. So thank you very much, and feel free to ask the questions.